Welcome to this explainer. Today, we're diving into something pretty wild, the actual architecture of time itself. Or, well, at least how we can mathematically manage time in really high-stakes environments. We're going to break down the structural architecture and state transition logic of the Dynamic Time Design Management app. If you've ever run a training session or hosted a big event, you definitely know that sheer panic when a schedule starts running over. Today, we're looking at how a specific application was built to handle exactly that scenario, and we're going to dig up the hidden architectural lessons buried right inside its code. So, let's jump in.
You know that feeling when an event is running late? For a good event MC, deciding what to cut is mostly just tacit knowledge. You just kind of read the room and know exactly when it's time to wrap up a heated debate or shorten a group exercise. But here's the tricky part. How do you actually capture that human intuition? How do we take something as fluid as reading a room and translate it into rigorous, mathematical, executable code? That is the exact massive challenge the developers behind this app had to face.
Here is our roadmap for today. 1. Formalizing time management. 2. Structuring the C4 model. 3. Detecting invariant violations. 4. Fixing the core logic. 5. Verification via LangGraph. And 6. Our conclusion.
Section 1. Formalizing time management. Let's start by looking at how the application formalizes the very real-world strategy of schedule buffering. It does this through a concept called float. Think of float like keeping a little extra emergency cash hidden in your wallet. The app gives facilitators two distinct modes to work with. First, you've got a tight packing mode with absolutely zero slack. Every single minute is strictly accounted for. But the second mode is a with float mode. This one intentionally keeps 10 minutes of buffer right there in your wallet to effortlessly absorb any unexpected delays. So if a session runs 5 minutes over, the float just absorbs it, and the rest of your schedule stays perfectly intact.
Section 2. Structuring the C4 model.
To see how this delay absorption actually works under the hood, we really need to zoom into the component level of the C4 model and check out the system's exact internal mathematical state. The crucial thing here is this really elegant 5-tuple, basically a 5-part data package. Every single transition function in this entire system revolves around this one package. It maps the overall time limit, whether we're using float or not, the array of fixed or variable modules, the available float pool, and the current delay. It is literally the beating heart of the system. Every click, every delay, every manual adjustment simply updates these 5 variables. But here is where the plot thickens. The app was recently updated to a new, quote-unquote, improved version, which was supposedly just adding some nice UI and UX polish. But when we compared the baseline code to this improved version, we discovered a massive change. That UI update had secretly reversed the system's trimming priority entirely. See, in the original version, if you completely ran out of float, the app mechanically cut the Q&A session first to make up time. But this improved algorithm flipped the transition logic to cut group work first, which ends up protecting the Q&A session. So, what was documented as just a simple visual upgrade actually fundamentally altered the core logic of how time was being managed.
Section 3. Detecting invariant violations.
And honestly, that wasn't the only surprise hiding in the new code. As we formalized these transition equations, we uncovered a pretty severe logic flaw hiding right inside the manual adjustment feature. When facilitators use the new feature to increase or decrease a module's time, like, let's say, adding 5 minutes to group work, the system wasn't just updating the current duration. There was an internal marker called original, meant to strictly record the module's absolute baseline time, and it was quietly being rewritten with every single click. Imagine trying to measure a piece of wood, but your ruler physically stretches every single time you use it. You would completely lose your frame of reference.
Now, in systems engineering, we rely heavily on invariants. These are the foundational rules that must always hold true no matter what. This stretching ruler bug caused 2 distinct invariant violations. First up, invariant 1. We had the mutation of a baseline value that absolutely should have been locked down. And second, invariant 2, the app had an upper bound check to ensure you couldn't extend a session for way too long. But mistakenly, this check was depending on that shifting broken original baseline instead of using fixed absolute constants.
Because of these 2 combined errors, we literally hit a brick wall at the number 30.
The system's operation manual actually included a practice scenario, Scenario 3, which told users to manually adjust a group work module from 30 minutes up to 35 minutes. But because the baseline kept rewriting itself and the upper bound check referenced that broken baseline, a module initialized at 30 minutes could never, under any circumstances, be extended beyond 30 minutes. The core manual adjustment scenario was completely broken right out of the box.
Section 4. Fixing the core logic. So how do we rescue the system? Well, the solution required us to cleanly untangle the display-level constraints from the data-level baseline values. The fix was actually incredibly elegant and deeply structural. First, we just entirely removed the line of code that was mutating that original property. The ruler was officially locked down. Then, we introduced absolute fixed constants to the system, a minimum duration of 5 minutes and a maximum of 60 minutes. Finally, we rewired the app's maximum time check to strictly reference those global constants, completely ignoring the module's initial baseline. By doing this, we successfully restored invariants 1 and 2.
Section 5. Verification via LangGraph.
Of course, in complex systems, we can't just cross our fingers and assume a fix works. To definitively prove it, we implemented the entire state transition model independently using a Python, LangGraph state graph. This is such a vital technique. By pulling the core logic out of the browser-based HTML and JavaScript app and rebuilding it in LangGraph, we got a purely mathematical, totally isolated environment. It let us dynamically verify that our invariants strictly held true during execution, totally free from any messy UI interference.
We mapped the LangGraph node flow directly to our C4 architectural blueprint, creating a really precise chain of transitions. You initialize the timeline, simulate a delay, trim the modules if your float is exhausted, manually adjust times if needed, and finally, render the state.
And brilliantly, the dynamic simulation proved the fix was absolutely perfect. When we ran the exact same sequence of events that previously failed, the module time seamlessly adjusted up to 35 minutes and then up to 40 minutes, all while the execution log definitively proved that the underlying original baseline remained perfectly unchanged at 30. The mystery was officially solved and Scenario 3 was finally possible.
Section 6. Conclusion.
Let's pull back for a second and look at the broader architectural lesson this entire bug hunt gives us, because it's about so much more than just a time management app. The crucial takeaway for any systems engineer working with stateful applications is that your transition conditions absolutely must be strictly separated from the mutable state variables they are designed to update. You have to cleanly separate your display constraints from your data baselines. Also, this explainer really highlights the danger of sneaking core logic changes inside what you document as UI improvements. And finally, by taking the tacit human knowledge of time management and formally modeling it, we exposed and fixed deep logical flaws that otherwise would have remained completely hidden in the code.
It's a structural challenge we all face when building interactive systems. So I'll leave you with this to think about. When you're designing your next architecture, how will you apply strict invariant documentation to formalize and protect your own complex code bases? How will you ensure your transition conditions are completely bulletproof? Thank you so much for joining me for this explainer, and I hope it changes the way you look at the hidden structure of the apps you use every single day.